Um, this video will be slightly shorter than our usual. Um, I just decided to give you some bit of a rest since you finished your exam yesterday. Okay. Um, Let us continue on sequences and look at what are called upper and lower limits. Upper and lower limits. Definition. Let Sn be a sequence of real numbers uh, with the following property. Be sequence of real numbers such that for every real number m there is an integer n. For every real number m there exists an integer n and belonging to n such that n greater than or equal to n implies Sn is greater than or equal to n. Okay, in that case we then write Sn diverges to infinity, okay, or plus infinity. Okay, similarly if for every m there in R there exists a n in naturals such that n greater than or equal to n implies Sn is smaller than or equal to m, then we then write Sn diverges to negative infinity. Okay, so some people say converges to positive infinity, converges to negative infinity. Some say diverges to negative infinity, diverges to positive infinity. Either of them is fine. We will still stick to the notation that the sequence is convergent only if it's finite. That is why I am saying these sequences are diverging to negative and positive infinity. Okay, some people just like to say converges if there is a number that it's converging to. So even if it's infinity, it's fine. You'll see that there are benefits to each of these. I might perhaps use it interchangeably. Feel free to use whichever method you prefer. Okay. Then definition. Let Sn be a sequence of real numbers. Let Sn be a sequence of real numbers. Let E be the numbers, E be the set of numbers in the extended reals. Let E be the set of numbers x in extended reals such that Snk converges to x for some subsequence Snk of Sn, for some subsequence Snk. Okay. Then E can potentially contain positive infinity and negative infinity. Okay. By definition of extended reals. Okay, we are allowing them to exist in E. Let us say that S upper star is equal to supremum of E, and S lower star is equal to infimum of E. Okay. These are called the upper and lower limits of Sn. S star, comma S lower star are called upper and lower limits of Sn, and often denoted by lim sup. Sn and lim inf Fsn. Lim infimum Sn is equal to S lower star. Okay. I will probably refer to them as lim sup and lim inf more than upper and lower limit. Okay. Because that is the more standard terminology, but calling them upper and lower limits is perfectly fine for the course. Okay, these limits are extremely useful, and we'll see why. Theorem 3.17. I'm going to omit let Sn be a sequence of real numbers. So actually, fine, I'll just write it down. Let Sn be a sequence of reals. Let E and S star be as above. Then S star has the following two properties. It's the following properties. Okay. A, S star belongs to E, and B, if X is greater than S star, then there is an integer N, then there exists N belonging to N, such that N greater than or equal to capital N implies Sn strictly smaller than X. Okay. Moreover, S star is the unique number with these properties. S star is the unique number with these properties. Similar results hold for S lower star. Similar results hold for S lower star. In particular, the only difference would be in the second condition, part B, if x is smaller than S lower star, then there exists an eigen in natural such that n greater than or equal to n implies Sn is actually greater than x, would be what the condition would read. Proofs are relatively simple. In fact, the major part of proof of part A is already done. We have seen that the set of limits forms a closed set, right? And so S lower star, which S upper star or lower stars, which are supremum and infimum of the sets, if the sets are closed, they will belong in the set. A very small problem with that proof is that it is not considering extended reals. This time we're talking about E being an extended reals. Okay, so we have to make two special cases. If S star is equal to positive infinity, then E is not bounded above. Then E not bounded above, right? Therefore, there exists some sequence which is not bounded, i.e. Sn is not bounded above. Above, i.e. there exists some subsequence Snk converge such that Snk converges or diverges, whichever way you want, converges to positive infinity. Okay. If S lower star, if S upper star is equal to negative infinity, okay, then E has only one element. Then E has only one element, negative infinity. Okay, and there is no other sequential limit. And no other sequential limit. Hence, what is the definition of it converging to negative infinity? For any real number n, there is at most do I even need to say this? He has only one element, and well, if he has only one element, then there is some sequence. Then Sn has. Then there is some subsequence converging to negative infinity. So, okay. Well, let me just write it down anyway. Hence, for every m there exists n such that n greater than or equal to n implies Sn smaller than m. and so Sn converges to negative infinity. Okay. If in the final case, if Sn is real, if S upper star is real, then E is bounded above. Then E bounded above. And at least one sequential limit exists. And at least one sequential limit exists. Okay. So A follows from the fact that it would be E is a closed subset, and that every the supremum and infimum of closed subsets belong to the set. So then A follows from which two things? Theorem 3.7 and 2.28. Okay. Now, part B is even shorter. Suppose there is a number x. Suppose there exists x greater than S star such that Sn is greater than or equal to x for infinitely many values of n. For infinite many values of n. Okay. Well, if you're looking at an infinite subset which is bounded, right, then you can either there is a subsequence which diverges, okay, in which case there should be a subsequence converging to positive infinity, then either the set of such x is bounded and an infinite subset of a bounded set has a limit point, in which case it has a limit point y greater than x, or it is unbounded, in which case some subsequence is diverging to positive infinity. Which case there exists subsequence this should have been Sn. Subsequence Snk diverging to infinity. Positive infinity. In either case, there exists a y in E star. That's right, E, such that y is greater than or equal to x is greater than Sn. No, that's right, S star. Contradicting that S upper star is supremum of y. Sorry, supremum of E. Okay. To show uniqueness, so this proves part B. To show uniqueness, suppose there is another number. There are two numbers P and Q satisfying A and B. P comma Q satisfy A comma B, and a P smaller than Q. Then there exists X between P and Q. P smaller than X smaller than Q, right? And since P satisfies B, there exists at most finitely many n for which Sn is greater than x. There exists, well, sure, let me say it the other way. We have Sn smaller than or equal to x, or strictly smaller than x, for n greater than or equal to n. The same n as part B. But then Q cannot satisfy A. Q cannot satisfy A. Okay? Because if there are only finitely many, then you do not have a subsequence converging to A. Let us look at some examples and some special subsequences, some special sequences, and stop when we reach series. Okay? Examples. A. Suppose Sn be the sequence of all rationals. Let Sn be a sequence of all rationals. Okay? Then every real number is a subsequential limit. Then every real number is a subsequential limit and limit supremum of Sn is equal to positive infinity, and limit n goes to infinity infimum. Sorry, so limit supremum of Sn is positive infinity, limit infimum of Sn is equal to negative infinity. Question: can I do this for a sequence of all reals? And I do this for a sequence of all reals. Okay. It's a really simple question. Think about why I can do this for a sequence of all rationals. Okay. And then try to come up with, can I do this for all reals? Second, that Sn is equal to -1 to the n over 1 plus 1 over n. Then the lim sup n goes to infinity. Sn is equal to 1, and the lim inf of Sn is -1. Okay. And third, which is more or less good enough to be a theorem or a corollary, but it's a direct observation, and we have talked about this before. So we'll just write it as an example. For any real valued sequence Sn, for a real valued sequence Sn, limit n goes to infinity of Sn is equal to S if and only if limit supremum n goes to infinity of Sn is equal to S and lim inf is equal to S. Lim inf n goes to infinity of Sn is also S. Okay? So this works both ways. If a sequence has the lim sup as well as lim inf as S, then that is the only number it converges to, so the entire sequence converges to S. Term 3.19. If Sn is smaller than Tn for some n smaller than or equal to, for every n, if Sn is smaller than or equal to Tn for every n greater than or equal to some n, where n is fixed, n is fixed, then limit infimum of Sn is smaller than or equal to limit infimum of Tn and limit supremum of Sn is smaller than or equal to limit supremum of Tn. Okay, so if a sequence is bigger, of course its lim sup and lim inf are going to be bigger. Okay. Proof. I'm not going to prove this. I'm going to leave this for you. Homework. Proof is rather trivial. Look at the set maybe E1 and E2 of all the sequences, subsequential limits of S and subsequential limits of t. Okay, and if you can show that one set has to be bigger than the other, you get your result. Not exactly bigger, but every element here has to have some element there which is bigger. Okay, so some special sequences these are sequences that are needed uh, constantly, and these will pop up, and so it's better to know their limits for all of them and have proofs. Okay, so we'll just write them down. Theorem 320, 320, A. If p is greater than 0, then the limit n goes to infinity whenever n to the p is equal to 0. Second, if p is greater than 0, then limit n goes to infinity, nth root of p is equal to 1. See? Limit n goes to infinity, nth root of n is equal to 1. D. If p is greater than 0 and alpha is real, and alpha any real, then limit n goes to infinity, n to the alpha over 1 plus p to the n is equal to 0. And E, if absolute value of x is less than 1, then limit n goes to infinity, x to the n is equal to 0. Proof. Some of these are extremely trivial. Others are slightly more non-trivial, but not really non-trivial. Part A. Take n which is strictly greater than 1 over epsilon to the 1 over p. Okay. Then this would mean n to the p is bigger than epsilon, is smaller than epsilon. Then 1 over n to the p smaller than epsilon. Okay, this is for any given epsilon. Take some epsilon, you can do this. B. If p is greater than 0, if p is greater than 1, let xn is equal to nth root of p minus 1. Okay? Then, well, if p is greater than 1, nth root of p is going to be greater than 1. So xn is greater than 0. Okay? And now I can use binomial theorem. And 1 plus nx n is smaller than or equal to 1 plus xn to the n, which is exactly equal to p. Therefore, 0 is smaller than xn, which is smaller than or equal to p minus 1 over n, which goes to 0. Therefore, xn goes to 0, which is to say the limit is 0. If p is equal to 1, then the result is trivial. Then trivial. If p is less than 1, take reciprocals of everything. Take reciprocals. Okay, so if p is less than 1, look at 1 over p. Nth root of 1 over p is equal to 1 over nth root of p. 1 over p is bigger than 1, call it q. Its nth roots go to 1, so the nth roots of p also go to 1. See? We want to show that the nth root of n goes to 1. So put xn is equal to nth root of n minus 1. Then again, by binomial theorem, we get that n is equal to 1 plus xn to the n is greater than or equal to n times n minus 1 over 2 times xn squared. Therefore, xn is smaller than or equal, which is strictly greater than 0. Actually, smaller than or equal to 0. If n is equal to 1, then this is 0. Is smaller than or equal to root 2 over n minus 1 and greater than or equal to 2. Okay? And therefore xn goes to 0. Therefore xn goes to 0. Therefore nth root of n goes to 1. D. Let k be a positive integer such that k belonging to n such that k is greater than alpha. Okay. Then for n greater than 2k, we have 1 plus p to the n is greater than, and choose k, p to the k, again by binomial theorem, which is equal to n times n minus 1 times all the way up to n minus k plus 1 all over k factorial. Well, n is greater than 2k, right? So this is greater than every single term is greater than k. Okay? What I'll do is I will say that if n is greater than 2k, and there are k of these, this is actually greater than n to the k over 2 to the k, since each is greater than k, right? Which is n over 2, times p to the k over, oops, I missed a p to the k here, p to the k over k factorial. Okay? Therefore, 0 is smaller than n to the alpha over 1 plus p to the n, which is strictly smaller than 2 to the k times k factorial over p to the k times n to the alpha minus k. And now, as alpha minus k is less than 0, and this whole thing depends on independent of n, as n goes to infinity, as alpha minus k is smaller than 0, n to the alpha minus k goes to 0 by a. Okay? And so the whole thing goes to 0, and hence my sequence goes to 0. For part E, take alpha is equal to 0 in D. Okay? So as you take alpha is equal to 0, you just get 1 over p to the n. And if absolute value of x is less than 1, you can find, you can write it as 1 over p, 1 over 1 plus p for some proper p. Okay? So we will not do series in this video. This is going to be a smaller video. We will cover series next time, okay? Which will, I think I can cover series in one class, which should, in that case, be the end of this chapter, okay? Oh, no, there are more things after series, so I was wrong. But we'll start series in the next class. Okay? So enjoy this short video.